So this is the content of today's webinar. We will first start with some background about electromagnetic radiation, what it is, and also some dose definitions. We will then move on to application, why we have electromagnetic radiation, and also some radiation protection. We then move to the RaySafe i3, the real-time dosimetry, and the different configurations of the systems. And finally, we will end with the questions, does it work? But first, let's start with some backgrounds. Electromagnetic radiation is moving waves of energy. The rays, or photon, as we also can call them, can be described as an interaction or interplay between an electric field and a magnetic field. It fluctuates with a frequency, which is related to the energy of the wave or photon. Electromagnetic radiation appears in many forms, and the range of the electromagnetic spectra is great, but it's only a very limited part that is visible to the human eye in the form of visible light. The wavelength of the electromagnetic radiation determines how it interacts with matter. For example, the light that we see is visible because it is reflected off the surfaces of objects around us. Some of the electromagnetic waves can penetrate materials. Based on the difference in energy, electromagnetic radiation is divided into two types: non-ionizing, such as the radiation in a microwave or radio signals, and ionizing, like the radiation from X-ray machines. Ionizing radiation has both natural and artificial origins, such as X-ray machines, radon, or cosmic sources. If the photon of the electromagnetic radiation has an energy of 10 electron volts or more, the radiation can be classified as ionizing. X-ray radiation can cause a physical process called ionization. If a photon interacts with a molecule in a specific way, an electron can be knocked out, leaving the molecule with a charge. A molecule with a charge is called an ion or radical, and is highly reactive with other elements around it. When an ion or free electron reacts, there is a risk the molecule gets damaged. The health effects of ionizing radiation are usually classified into two categories: deterministic and stochastic. According to the International Atomic Energy Agency, IAEA, a deterministic effect is a health effect that requires a specific dose level before it can occur. The severity of that deterministic effect increases as the dose exposure increases, and there is a minimum threshold below which no detectable clinical effects occur. This type of effects is predictable and reproducible. For example, localized doses to certain parts of the body at known radiation level will result in the same biological effects. Deterministic effects are caused by severe cell damage or cell death. Individuals who experience the physical effects of this cell death do so when it is large enough to cause significant tissue or organ impairment. Stochastic effects are probabilistic effects that occur by chance. A rare stochastic effect is the development of cancer in an irradiated organ or tissue. The probability of occurrence is typically proportional to the dose received. Stochastic effects after exposure to radiation occur many years later, the latent period, and the severity is independent of the dose originally received. Since many agents in the environment are also known carcinogens, and since many cancer occurs spontaneously, in most cases it is not possible to directly link a specific radiation exposure to an observed cancer. If a population group receives a dose of ionizing radiation at one time, it is not possible to predict who in that group will develop cancer, if any, or to state that the people who develop cancer did so because of the exposure or some other lifestyle factors such as smoking. But one can say that on a group level, the probability of cancer increases with increased radiation dose. To be able to define the biological effects of radiation, one has defined different dose definitions. We have the absorbed dose, capital D, which is defined as the mean energy the radiation transmits to a volume with a specific mass. Since the human body is inhomogeneous, one needs to define a mean absorbed dose, which is dT. This dose is a measure of energy released or ionization in that volume of mass. But it does not tell us anything about the biological effect of the radiation. Different types of radiation have different effects on biological tissue. For example, alpha particles are relatively large particles and will interact with tissue in another way than X-rays. To catch this phenomenon, one has defined the equivalent dose. Equivalent dose represent the stochastic health effect of low level of ionizing radiation on the human body, which represents the probability of radiation-induced cancer or genetic damage. Different parts of the body are also more or less sensitive to radiation. Reproductive organs and breast are more sensitive compared to fatty tissues. If a specific organ is irradiated, one has defined effective dose. To protect us from these stochastic effects, radiation authorities all over the world have defined annual dose limits. These are limits authorities believe are associated with acceptable small enough risks for genetic effects. People who work in an environment with radiation have substantial higher limits compared to the public. It is impossible to completely shield us from the radiation, and the risk is never zero. These limits are the reason why medical staff or staff in other radiation environments need to wear dosimeters. One could think that most dosimeters are measuring effective dose, but this is usually not the case. When you get exposed, for example, from scatter radiation, it is impossible to say which organ received which dose. One is therefore using an equivalent dose corresponding to personal dose. This can be specified at different depths in the body. For example, HB 0.07 is the superficial or skin dose, and HB3 is usually used for the eyes, and HB10 is the most used dose unit. If I am using low energy photons, I would need to use a dosimeter that catches dose to the skin, since most photons will be absorbed in the skin. In that case, I should have a skin dosimeter, an HP 0.07. If I work with higher energy photons, I need a dosimeter that catches dose penetrating further into the body. Even if effective dose tells us more about how radiation is affecting us, it is not easy or practical to use such a dosimeter. Common practice is therefore to report personal dose equivalent to the dose records. Personal dose equivalent is always higher than effective dose, meaning it is more conservative to use personal dose equivalent. And being conservative is usually a good approach when it comes to radiation protection. Let's start with the second part of the webinar called the application. Now we're going to talk about application in which medical staff are exposed to high doses of X-ray. Image-guided surgery is commonly used in interventional radiology, cardiology, and hybrid operating theaters. When an exposure happens, it will be scattered radiation all over the room. The patient always gets the highest dose during the procedure, but staff, on the other hand, are exposed to some amount of radiation every day, and the accumulated dose over years can be quite high. It is therefore important to control the environment also from a staff perspective. Most of the time, staff is placed on the right side of the patient. This means that the staff closest to the patient has its left side of the body closer to the patient and the radiation source. It is also common to lean forward towards the patients, increasing dose to head and eyes. The three main parameters for radiation protection are time, distance, and shielding. Depending on which role you have in the operating room, you will have different possibility to work utilizing these three principles. We believe that if you get instant feedback on your absorbed dose, it will be a lot easier to change behavior and working procedures. If you are used to one way of working, it is hard to change it unless you understand how a change will affect your dose. There are many effective shields out on the market. There are lead curtains protecting the staff's lower region. There are lead glass shields used for general shielding. Staff often wear lead glasses to protect their eyes, and staff also wear lead aprons for overall body shielding. Shielding can sometimes create a false sense of safety. Different shields are not equally efficient. Parts of the body may not be fully covered. There is no known safe dose level, so one should therefore always try to decrease the dose to a minimum. Depending on setup in the operating or surgery room and status of the personal protective equipment, the following areas can be worth having a closer look at. Number 1, the lower region. There are lead curtains protecting staff's lower region, but there are always some radiation passing through. Lead aprons also usually ends around the knees, making the lower parts of the body more exposed. 2. The eyes. It is common for the staff to lean forward, placing the head closer to the radiation source. The legal dosimeter is usually placed on the chest, further away from the source. This can create a discrepancy between the registered dose and the actual dose to the eyes. Some staff use smaller eye dosimeters placed on their lead eyeglasses, but eye retinas are among the more sensitive body parts, and legal eye dosimeters only register already absorbed dose. 3. Breast. Most lead aprons are designed for men. For women, there might be a gap on the side exposing the side of her breast, especially on the left side, since that side is most often facing the patient. The breast contains radiation-sensitive tissue and glands. Legal dosimeters are necessary, but the main drawback of these passive devices is that you will find out about your dose afterwards, after you have already received the dose. If one could have a real-time dose feedback, one could have made corrective actions in the setup and behavior during the actual procedure, heavily increasing radiation awareness and decreasing dose. So now let's move on to the third part, the real-time staff dosimetry, RaySafe i3. In reality, it can be difficult for the medical staff to judge how they are doing while in the middle of a procedure. That is why RaySafe developed real-time dosimetry. The real-time dosimetry, such as the RaySafe i3 system, will show personal dose rates in real time, visualized as colored bars. With this information, users will be able to tell when and how much they are being exposed to, and whether any dose reduction measurements are effective. In other words, it will help to illustrate the concept touched upon in the previous slides. Over time, this helps user build a better intuition, adapt and learn what works and what doesn't, in terms of keeping radiation exposure as low as reasonable achievable. To start with, let's have a closer look at the dosimeter itself. We have two different versions of the i3, the standalone display and the OSD, which stands for on-screen display. On the left-hand side, you can see the standalone installation. It is a separate screen which can be placed more or less anywhere in the room where it is convenient for the staff. On the right-hand side, you see our OSD version. In this setup, the view is integrated with a big operator screen, together with other important procedure data. If we start looking at the standalone display system, this is the easiest and most versatile solution. You have a display that can be mounted wherever you find it suitable. For basic functionality, it only requires a power supply. As soon as you pick up a dosimeter, it starts to communicate with the screen, and the dosimeter will appear on the screen a second or so later. A total number of 8 dosimeters can be shown on the screen at the same time. When radiation is picked up by the dosimeter, the dose rate is visualized as a moving colored bar on the screen. The screen is updated every second, so you can easily follow how your movements or actions affect your dose rate. Data is stored on the dosimeter itself, but it has some limitations compared to the screen. The screen will save all data for all dosimeters, and the memory is big enough for you to never have to worry about losing any data. If you would like to export dosimeter data from the screen, you have 2 options. You can either insert a USB on the back of the screen and extract it, or you can have it connected to the local network and pull the data from our dose manager software. Our on-screen display is our most refined solution. Our system is integrated with the X-ray machine, which gives other possibilities compared to the standalone display. Depending on how it is integrated, the RaySafe i3 view can be displayed on one or several of the big screens in the operating room or in the control room. The size and the position of the view can usually be customized to make sure that all personnel would have as good view as possible. You also have the possibility to add a reference dosimeter, which is placed directly on the X-ray machine. I will talk a little bit more about this reference dosimeter in a few minutes. Just as with the standalone display, as soon as you pick up a dosimeter, it starts to communicate with the system and will appear on the screen a second or so after it has been picked up. All dose data is saved in the real-time hub, and you can easily pull data from the hub through a web interface, or you can pull the data from our dose manager software. The OSD system mainly consists of 2 different units. One is the real-time hub, which is mounted somewhere in the operating room. It communicates with the dosimeter and stores all the data. Data is sent to a video unit, usually placed in the X-ray system's technical room. The video unit is connected to the X-ray system and enables visualization of colored bars on the big screens in the operating room. Let's talk a little bit more about the reference dosimeter. It is placed on the X-ray machine. It is not shielded in any way, meaning it will always register dose as soon as there is radiation. And this makes it possible to do other types of dosimeter data analysis. For example, if we have one staff dosimeter used during a procedure when it's well shielded, it will not register any dose. If you only look at that dosimeter data, you cannot tell how many exposures there's been. You will only see how many exposures you received dose from. With a reference dosimeter, you can see which of all exposures you were well shielded from and which you were not. Based on this, you can see which actions could be targeted for dose reductions and which would be harder to improve. Let's do a demo to show how i3 visualizes radiation. The first thing we do is to pick up the dosimeter, and after a few seconds, it will appear on the screen. Then we place the dosimeter in the radiation field, and then we can see how colored bars visualize the dose rate. Let's start with the distance principle. We increase the distance from the source, and the dose rates decrease quite a lot. Then we can also add more shielding, and the dose rate will decrease even more. A few words about our two software, RaySafe Dose Viewer and RaySafe Dose Manager. Dose Viewer is our free software. When a system is bought, it will be included on a USB in the package. It is also downloadable from our webpage. This software gives you basic dosimeter functionality and is required for the initial system configuration. By connecting the dosimeter to your computer, you will get an overview of the dosimeter dose data. But there are some more features if you press dosimeter options. One can change name, color, and other general information about the dosimeter, and also the power options for the dosimeter. When power mode is on, it works as usual. When the dosimeter is picked up, the accelerometer will wake the dosimeter up, and it will go to sleep if idle for a while. Power mode off means that it is always turned off. This might be especially good during transportation of the meters. There is no reason for them to wake up during transportation. When pressing advanced, there are a few interesting options as well. Always on is self-describing. It will never go to sleep. The last option is an extra feature we recommend using, even if the batteries are consumed faster. We have seen that if dosimeters are dropped or shaken hard, this may be interpreted as dose. By activating this option, false readings will be filtered out. The settings we recommend using is Advanced Suppress False Readings. RaySafe Dose Manager is a more advanced software one can purchase. It has the same but also additional features compared to RaySafe Dose Viewer. RaySafe Dose Manager is useful if you would like to compare dose data for several dosimeters at the same time. If a standalone display and real-time hub are connected to the local network, one can pull dose data for all dosimeters and all systems into one single database. One can easily compare dose data between different operating rooms or operating teams depending on the setup. In-depth analysis like this makes it easier for staff to learn from each other, to understand why one team received less dose than another, even if they are doing the same procedures. But does it work? Yes, I'm very confident that it works in decreasing dose to the staff. I will now show you some real-life situations where i3 has helped our users. In this first case, we had a Dr. Smith. Dr. Smith forgot the movable shield while focusing on the procedure. Miss Ranger alerts Dr. Smith that her bar is red. Dr. Smith positions the shield properly, and the next pedal press, the bar is much lower. Real-time dosimetry reminds users to use their existing tools and knowledge, for example, room shields. And real-time dosimetry encourages teamwork and helps build a radiation safety culture. In the second case, we are focusing on Miss Burrows, one of the staff members in the operating room. Miss Burrows is standing in a spot she thought was safe. RaySafe i3 shows that she's getting high readings. Miss Burrows takes a few steps back or stands behind the operator, and the yellow bar goes down. Scatter fields cannot be seen, and it can be difficult to predict. Real-time dosimetry confirms whether the action taken was effective, which promotes learning. In the third one, we're following the soon-to-be interventional cardiologist, Dr. Johnson. Dr. Johnson is about to become an interventional cardiologist. She's very focused on the patient in her educational sessions, and is using a high frame rate and long exposure times to make sure she has a good view of the patient. RaySafe i3 shows high readings. The more experienced tutor discovers the high dose rate readings and reminds her to lower the frame rate in certain parts of the procedure. Real-time dosimetry can be a helpful tool when coaching team members in radiation safety. There are, of course, many more situations in which I3 can be of great use. But what does the science say about our products? Can we actually prove that the real-time dosimetry works? There are several studies out there involving I3, and they are increasing in numbers for every year. I have selected 4 different studies to talk a little bit more about. In this American study, the monthly OSL dosimetry records obtained during the 8-month period before introduction of real-time dosimetry were set as a reference. This reference was then compared to a similar 8-month period after the implementation of real-time dosimetry. They experienced a big decrease in dose for all staff in the operating room. The physician decreased by roughly 66%, the nurses by 43%, and the technologists reduced their dose by 45%. In this second Swedish study, the medical staff working in the cardiology laboratory consisted of 3 cardiologists and 10 nurses, and all staff members participated in the study. During each procedure, radiation dose data was collected for the cardiologist and the rest of the staff members. The measurement period was divided into 2 data collection periods of 1 month each. During the first period, the personal dosimeters and the reference dosimeter registered the radiation dose, but the dose rate information was not displayed, only stored for analysis. During the second period, the system was used to its full extent and the radiation dose rate information was displayed. They saw a decrease of roughly 40 to 60% on all staff members. In this third German study, a total of 270 coronary procedures were performed in one of the 2 cardiac cath labs. All procedures were exclusively performed by experienced cardiologists with at least 500 cases as a first operator. No educational angiographies or interventionals were included. Importantly, no changes in procedural strategies were allowed in order to prevent changes in dosimetry results not related to optimizing shielding and/or staff behavior. In the first part of the study, operators and assisting staff were individual dosimeters without access to the results inside the cath lab, called the blinded period. While in the second period, the system was used with instant visualization of the radiation exposure results for all staff members, the unblinded period. And one can see a big decrease in dose. Medical staff, roughly 40%, the radiologists, almost 70%, and other technologies, almost 50% reduction. Real-time dosimetry effectively reduced staff radiation exposure in the cath lab. This change was caused by optimized use of existing shielding equipment since no modification of the general procedure approach or patient characteristics had occurred. The fourth study was approved by the Institutional Ethical Committee. This study consisted of 2 phases. For 5 months, staff did not receive personalized dose feedback and dose data for each procedure was prospectively collected. And the next 3 months, staff received weekly individual personalized dose feedback. After 8 months, the dose feedback was evaluated anonymously through questionnaires. And it is clear that staff, if you look at the purple and dark blue numbers, appreciated the dose feedback that helped them to increase radiation awareness and self-protection, enabling them to feel more secure at work. We have, of course, received plenty of good feedback from hospitals all over the world, and it's clear that RaySafe i3 really helps staff reduce their dose and make them feel more comfortable and safe at work. A few months ago, ESVS released new guidelines recommending the use of real-time dosimetry. They find it really powerful and say it should be considered for all endovascular operating rooms. This is just another proof that RaySafe i3 has made a big impact on creating radiation awareness for increased staff safety. This concludes today's webinar, and I would like to thank you for participating today. Hope you found our session useful.
I would also like to thank you, Patrik, for a fantastic presentation, and a huge thank you also to our audience today. Attached to this webinar and on our website, raysafe.com, we will find even more information. Now it's time for the questions and answers section, and you're encouraged to join us and share your questions.
We have received some very interesting questions from the audience today. Unfortunately, we have some technical difficulties disabling us to use the webcam, but we are here with you. So, first question received is, I have an i3 standalone display. Is it possible to mirror the view to another screen?
It is not possible with the standalone display. If you have the on-screen display version, there are two options on how to mirror it. First one is to use an HDMI splitter and have a secondary HDMI cable routed to another screen. The second option could be to use the web interface. If you have a computer on the same network as the OSD system, you can log into the hub using your web browser. And when logged in, you can see the same view on your computer monitor as shown in the big operating screen.
What is the dose scale shown on the i3 screen, and why have you chosen it?
The scale on the screen is a 10 logarithmic scale. The green portion is between 0 and 0.2 millisievert per hour. The orange part is 0.2 to 2 millisievert per hour, and the red part is between 2 and 20 millisievert per hour. And the reason we have chosen a logarithmic scale is mainly because changes in dose rate can be huge when you take a step back or hide behind a shield or something like that. And to capture these huge changes, a logarithmic scale is needed. If we were to have a linear scale, the screen needs to be like 100 times longer to be able to visualize the same progress, which is, of course, not feasible.
Okay, does it matter where and how I wear the i3 badge?
Yes, you will get very different results depending on where you wear it. We often get questions if it should be worn inside or outside of the lead apron. Many would like to have it inside of the lead apron to see how much dose the body gets behind the lead. But that is not our intended use. If you wear it behind your lead apron, you will get extremely low readings. It will therefore be hard to make smart decisions to decrease your dose if it already looks like it's 0. Even if you have the lead apron, you will still have a lot of your body still exposed, like the arms, hands, and face. So we believe it should be placed on the outside of the lead apron and somewhere showing a worst case scenario without being in the way of your work, of course. Or you can have it at a position you personally have a concern about. And where this position is up to the user to decide. We have examples of users wearing it on the neck collar to capture radiation to the face. We have examples of people wearing it on his or her left shoulder, since that side is mostly facing the patient. And the other, you just have it close to the chest. So it all comes down to the user's preference.
Can I have a reference dosimeter for the stand-alone display?
The reference dosimeter is only available for the OSD, the on-screen display version. So no, you cannot have it for the standalone display.
What is the difference between RaySafe i3 package on-screen display and RaySafe i3 package?
I believe the difference is just the OSD version versus the standalone. So we only have two versions of the i3. It's the standalone system, standalone display system, and the OSD system.
What is the difference between i3 and RaySafe X2?
These are two completely different product families. So the X2 is used for quality assurance testing on X-ray machines, and the i3 is an educational tool or a help for staff in cath labs, for example, to create radiation awareness. So they are two completely different product lines.
How do I know if the battery is low on my i3 dosimeter?
There are a few ways, but some ways are easier than others, depending on which system you have. Each dosimeter has a LED light indicating the battery level. Every time you activate the dosimeter, it should make a quick flash. So green light is okay, orange is slightly depleted, and red means that it's low. If you have the standalone display, you can press on the dosimeter on the screen, and the screen will tell you the battery level. On the OSD version, a low battery indicator will show to the right of the dose bars if you do not have any reference dosimeter present.
Can we use dose manager software with X2?
No, that is not possible. Dose manager is only for communicating with either the standalone display or the real-time hub, so it can only be used with i3.
Okay. So, anything else you would like to know from us? I believe it's time to wrap up then and get back to you with answers that you may have after the webinar.